Low. Every time the lights went out in the house, someone had to go find the fuse box, feel around in the dark for the blown fuse, and then find a replacement, assuming one was on hand. If it wasn't, the circuit stayed dead until morning. That was not a rare emergency. That was Tuesday. For most of the 20th century, a blown fuse was simply the price of electricity at home. The fuse was, by design, a sacrifice. A thin metal wire or strip sat inside a small cartridge or screw-in plug, and when too much current pushed through the circuit, that wire melted. The circuit opened. The current stopped. The house was safe, and completely in the dark until someone physically replaced the part. The fuse did exactly what it was designed to do. The problem was what it demanded from the person on the other end. That sacrificial design made sense when electricity was new. The fuse's entire purpose was to be the weakest link on purpose, to fail before the wiring in the walls failed, before heat built up inside insulation, before a fire started inside a space nobody could see or reach. A metal strip that melts at a known current threshold is a remarkably elegant solution to a genuinely dangerous problem. The constraint wasn't laziness or poor engineering, it was the operating logic of early electrical systems. Accept a small, cheap, replaceable failure to prevent a large, expensive, catastrophic one. The distribution board, the panel that divides incoming electrical power into separate circuits for different parts of a building, was built around this logic from the start. Each circuit got its own fuse. Each fuse was rated for a specific current load. Exceed that load, and the fuse blew. The system worked, but it created a recurring maintenance task embedded in ordinary life, and it carried a secondary risk that took decades to fully appreciate. A blown fuse is an honest failure. A replaced fuse hiding a deeper wiring problem is not. The real constraint was not the fuse itself. It was the reset. A melted wire cannot unmelt. Once a fuse blew, the only way to restore the circuit was to remove the spent component and install a new one. That process required physical access to the panel, the right replacement fuse of the correct rating, and the awareness not to install a higher-rated fuse just to stop the nuisance of repeated trips. That last temptation was the most dangerous part of the whole system. A fuse rated too high for the wiring it protected would not blow when it should, and the wiring in the wall would absorb the excess current instead, heating up in a place no one could monitor. The circuit breaker solved the reset problem by replacing the sacrificial wire with a mechanical switch that trips under overcurrent and can be manually reset without replacing any part. Instead of a metal strip that melts and is gone, a breaker uses the physical effect of excess current, typically the heat generated by that current, or the magnetic force it produces, or a combination of both, to flip a switch open. The circuit interrupts. The hazard stops. And when the underlying problem is corrected, the switch can be pushed back to the closed position. Same panel, same location, same circuit. No replacement part required. That mechanical action is the core of what changed. A bimetallic strip inside the breaker bends when it heats up under sustained overcurrent, and that bending releases a latching mechanism that snaps the switch open. For short, sharp surges, the kind produced by a short circuit rather than a prolonged overload, an electromagnetic coil responds to the sudden spike in current and trips the mechanism much faster than heat alone could. The two responses cover different failure modes within a single device, which is why a circuit breaker could replace the fuse without asking the building to give anything up in terms of protection. The distribution board adapted accordingly. Modern panels are built around breakers rather than fuses, with each circuit assigned a breaker of the appropriate amperage rating. The main switch that controls all circuits feeds into the individual breakers, and more recent panels incorporate additional protective devices alongside them. Residual current devices, also called ground fault circuit interrupters or RCCBs, detect a different kind of failure entirely. A standard circuit breaker responds to overcurrent in the circuit. A residual current device monitors the balance between current flowing out through the line conductor and current returning through the neutral conductor. When those two values are not equal, current is escaping somewhere it should not, possibly through a person. The residual current device trips the circuit faster than the human nervous system can respond to the shock. That distinction matters because it reveals the limit of what the circuit breaker, on its own, actually fixed. The breaker solved the reset problem. It made overcurrent protection reusable and removed the temptation to defeat the system with an oversized replacement. But a circuit breaker cannot detect a small current leak to ground. It cannot distinguish between a proper circuit and one where a fraction of the current is passing through someone who touched a faulty appliance. The residual current device closes that gap, but it works on a different principle, responds to a different hazard, and was developed as a separate layer of protection added to panels that already had breakers. The cost of the transition from fuses to breakers was not technical. The mechanism was understood well before breakers became the default in residential construction. The cost was standardization and code. Building codes had to specify breaker panels. Electricians had to be trained on the new hardware. Manufacturers had to produce breakers at the price point where they could displace fuses in new construction without resistance from builders watching material costs. That process did not happen overnight, and it did not happen uniformly. Fuse-based panels remained common in older housing stock long after breakers became the standard for new builds, and they remain in place in some older homes today. That uneven adoption is worth sitting with because it tells you something about how safety improvements actually spread through built environments. A circuit breaker installed in a new home in 1 decade does not automatically upgrade the home built 2 decades earlier. The older home keeps its fuse panel until the panel fails, until a renovation triggers a code-required upgrade, or until the owner chooses to update it. The improvement in the standard does not reach everyone at the same pace. It moves at the speed of construction cycles, renovation decisions, and enforcement, which is to say, it moves slowly and unevenly through the real world, even when the technical case is clear. The behavior change that followed the circuit breaker was quieter than the technology itself. Tripping a breaker became something people reset themselves without calling an electrician. The panel became more accessible, more legible. Each breaker labeled for the circuit it controlled, the tripped breaker visually distinct from the live ones. Electrical faults that once required a replacement part and a trip to the hardware store became, in most cases, a 2-second fix. That shift redistributed a small but real friction from everyday life, and it also changed what people paid attention to. A blown fuse was an event with a physical object to show for it. A tripped breaker is a switch to flip. Easier to reset, but also easier to reset without asking why it tripped in the first place. The central question this episode opened with was why replacing a fuse became resetting a breaker. And the answer is not simply that one technology was better. It's that the fuse contained a structural contradiction. The same feature that made it safe, the sacrificial wire that had to be replaced, also created the conditions under which people defeated it. The circuit breaker eliminated the replacement step, and with it, the temptation to install the wrong fuse. What replaced the fuse was not just a more convenient device, it was a design that made the safe behavior the easy behavior. The residual current device added to modern panels is the next chapter in that same logic. A layer of protection the breaker alone cannot provide. watching for the kind of fault that doesn't trip the overcurrent switch, but can still kill someone. The panel on a wall in most homes today is a layered system, each component addressing a failure mode the previous one couldn't reach. The fuse started that system. The circuit breaker made it maintainable. The residual current device made it responsive to the human body in the circuit. The constraint that produced each step was the one the previous step left unsolved. Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.